I am excited to introduce our bonus project, implementing RDT3.0, a sliding window protocol with selective repeat for enhanced efficiency and basic security measures during file transmission. Since the code will be implemented from scratch, our first task in Part A is to create an unreliable transmission network that supports packet corruption, loss, and delay simulation. Once this network is established, we can proceed to implement RDT 3.0. Finally, we will design test cases to ensure the correctness of Part A. In Part B, we will parse the inputs and implement the algorithm. We will also perform a performance profiling with an increasing window size to demonstrate the effectiveness of our approach. As usual, we will verify the correctness of our implementation. In Part C, we will implement a customized public and private key encryption for identity authentication. Furthermore, we will introduce content encryption and simulate a hacker attempting to attack the file transmission process. Our authentication protocol will reject invalid users and protect the file contents. To simplify input management and streamline testing, we utilize YAML files to parse user inputs. Conveniently, each YAML file serves as a corresponding test case. Additionally, our code automatically logs simulation results to a designated folder with the same name as the configuration file. Here's an example of how to provide input parameters for our program. We parse the input YAML file and convert it to a C++ struct to facilitate the handling of user inputs. The user can control the probability of packet delay, loss, and corruption, allowing for a comprehensive simulation of an unreliable network. In addition to the previously mentioned parameters, there are other simulation-related parameters that are important to consider, including round-trip time, RTT, maximum delay in milliseconds, and window sizes. FNAME is the file that the server will send to the client. OFFNAME is the path that the client will save the received file. HackerFNAME is the path where the hacker will save the copied file. To build an unreliable network simulator, our system supports unreliable send and reliable receive, along with the following features. Our system asynchronously receives and delivers packets to ensure the independence of sender and receiver. The unreliable system stochastically simulates the packet transmission process. The simulator can precisely simulate packet delivery in milliseconds. The detailed simulation design is shown by this figure. The server, client and network simulator are running independently. A shared event queue is used to process the packets in order. The client and server will be notified when the packets are ready. The dispatcher randomly selects some behaviors when handling each packet. Here are some key codes that are used to implement our simulator. To implement the Reliable Data Transfer Protocol RDT 3.0, we closely follow the state machine. Our implementation includes various essential components such as checksum to detect corruption, ACK for communication synchronization, sequence number for various usage, and a timeout mechanism for retransmission. To test the robustness of our program, we have prepared several comprehensive testing cases. Specifically, for Part A, we have tested our program with 3 different files of varying sizes under various unreliable conditions to ensure that our program can handle all possible scenarios. Here are the log results for various test cases. In the first test case, with perfect reliable conditions, there were no lost, delayed, or corrupted packets during the transmission. In the second test case, we set the probability of corruption to 10%. Finally, we tested the simulator under different scenarios such as delay, packet loss, and a hybrid case where corruption, delay, and loss may happen jointly. Here is a demo of our program in action. In a perfect transmission system, the file can be transferred without any issues. However, we also tested our implementation under various unreliable conditions such as packet corruption, packet loss, packet delay, and combinations of all 3. Our implementation was able to successfully handle all of these cases, ensuring reliable file transmission. We conducted performance profiling to evaluate the impact of different unreliable behaviors on file transmission. The x-axis represents the probability of each behavior, and the y-axis shows the total transmission time. Our results show that packet loss significantly slows down the transmission compared to packet delay and corruption. One possible explanation for this result is that the sender needs to continuously retransmit the packet until timeout in case of packet loss. In Part B, we implement sliding window with selective repeat to improve the utilization. The new input is the window size. The sliding window keeps sending the packets with the available sequence number in window. As shown in the code, the sender always makes sure there are n packets in transmission. The core part of selective repeat is that the sender only sends timeout packets for retransmission. The sender only handles ACKs with sequence number inside the current window size. Other packets are ignored. The received ACKN will be marked. If the sliding window can move forward, the sender will try to move as far as possible. The receiver only handles packets with sequence number inside the current window or previous window. If the packet is in the current window, we need to reply ACK, buffer the out-of-order packets in memory for later use. If the buffer is in order, the client delivers the data and try to advance the window forward as far as possible as well. If the packet is in the previous window, then the client has processed the received packet. Just need to reply the ACK to make sure the sender receives the acknowledgement. To support the sliding operation easily no matter in the sender or the receiver side, I design a specific sliding window data structure. This data structure needs two handy features. First, it should flexibly slide the window forward. Adding one more element, remove the old element and make sure the indexing is correctly updated. Here is my implementation. The pushback function supports easy sliding operation. The indexing then is correctly handled. We present our performance profiling results in two figures, which were obtained under a hybrid unreliable transmission condition. The x-axis denotes the window size, and the y-axis represents the total transmission time. The left figure is for a medium file, while the right figure is for a large video file. As the window size increases, we observe a significant decrease in transmission time, especially for small window sizes. However, as the window size continues to increase, the transmission time gradually converges, as shown in the figures. To verify the correctness of Part B, we also provide many testing cases with different file sizes and different window sizes. All the testing cases are under unreliable transmission conditions. Let's see the demo. Here is an example of window size that equals 1, in which case it degrades to stop and wait. The demo further shows another example with the same file, same network condition but with window size equals to 4. In Part C, we need to implement identity authentication and content encryption. The new input parameters are the public and private key pair and if the encryption is enabled. Our customized public and private key authentication algorithm works in this way. First, the public and private key pair sums up to 256. If the private key is 133, then the public key is 123. For identity authentication, we first use the public key for encryption. The result is 211. The client then uses the private key to decrypt the value. The result is then 88. As the 88 is the same as the input, the identity authentication passed in the example. We also need to simulate a hacker that may be able to sniff all the packets received by the receiver. In the simulation, the hacker received the same packet received by the receiver and save the packet into a file. To protect the data transmission, we further implement a content encryption algorithm. If it is implemented correctly, the hacker should dump a garbage file instead of a copy of the file from the receiver. For simplicity, we use an exclusive or trick. The trick is that if we apply the exclusive or operation twice with the same value, the input value can be recovered. Here is an example. Apply the exclusive or operation twice to the A can result the same value as A. To verify the correctness, we design 9 testing cases for the Part C with different file sizes. For each case, we test if the authentication works, if the content encryption works. Demo time. The first testing case shows if the public and private key is not a pair, the system detects the error and rejects to proceed. The second testing case shows that the hacker can save a copy of the file that the client receives without content encryption. The third testing case shows that the file contents are protected with content encryption. There are two ways to test the code. The first way is easy to play with. Just run the program and use the YAML configuration file as input. A more scalable way to test the cases is to run the run all Python script. It can run all the testing cases for all parts, individually or all together. The result is saved in the corresponding log folder. The log folder has similar directory structure with a configuration directory. This pair of image is an example.